Hey folks, thanks for watching yet again another Murphy video, this one on section 6.3b. 6.3a dealt with the binomial distribution. It was introduced and you talked about how to find probabilities related to a binomial random variable. And this section is going to expand upon that a little bit by talking about finding the mean and the standard deviation of the binomial distribution. I'll start off with a harder type of binomial problem too, and then just additionally go over the things we would need to demonstrate in order to receive AP credit on such a problem if we are exposed to it on the AP test, which you probably will. And then finally, we'll conclude things by looking at a geometric random variable, which is a different type of distribution that's actually much simpler than binomial. What I want to acknowledge first, though, is that the page that I started on is only the second page of the document, and the first page, which would have been a do now had we been in person, reinforces some concepts from 6.2, which was kind of giving you situations that compared the notion of a linear transformation on a random variable versus a combination of a couple random variables. So it may be a good idea to not skip this over entirely. It's not related to the section, but when you're looking back at the note key in retrospect, maybe try looking at that problem, make sure you can do it, make sure you know the difference. But anyway, moving onward and forward with binomial stuff. So I was curious about this. I actually did Google. I figured the answer to this would be fries. As it turns out, it is public information that French fries are McDonald's #1 most popular menu item, of course. I wanted to know what proportion of orders, though, contain French fries. I imagined it would be most, but maybe not an overwhelming amount, because they probably don't serve them during all hours of the day and whatever. But anyway, that information is not out there. At least I couldn't find it. If someone can, let me know. But I just took a guess and said, let's say that 60% of purchases made at McDonald's include an order of French fries. So if there were an SRS and it were to select 10 random receipts from various McDonald's locations, I want to know the probability that more than half of them would contain an order of fries. So first, while you're kind of mulling over this problem, take a second to read the bottom part and see what you would need to show for a binomial-related problem on the AP test in order to receive full credit. This rubric came from the 2019 exam, which is recent enough that we can probably bet not much has changed. So it's pretty much the same stuff. And I also know we're in section 6.3, so it's obvious now that this is a binomial problem. But if it weren't obvious, because on the AP test it's literally just everything, you would need to state that the distribution that we're looking at is a binomial one. You'd have to identify that we are working with a binomial distribution. If we're creating a variable out of thin air, we need to define it and say x is a binomial random variable with this trial size and this probability. These numbers are made up because they came from the AP test, but whatever, you get it. So that's thing number one. Identify as binomial, list your parameters. Thing number two is to identify the correct boundary region. That's usually what I refer to in class as the probability statement. The probability that x is less than or greater than or whatever. Something like that, because that kind of reinforces what area under the curve or what area on the distribution we're looking at. And then, yeah, for number three, we got to get the right answer. Make sure you don't fall into any of the traps of doing something that would only earn you partial credit, and if you get an I, you probably just don't even know what you're talking about. But anyway, to do this from start to finish, we should acknowledge here, I'm defining a random variable called x. I'm going to let it equal the number of fry receipts out of the 10 receipts that are selected in the SRS. So x is a binomial random variable. We don't necessarily need to state this, it might be obvious, but we talked about a couple things that would necessitate a binomial setting here, and we don't quite have independence because there's only so many receipts that McDonald's can have per year, but we're going to say that the pool of receipts is so large that every selection is practically independent. So independence, check, we got it. This is a binomial situation, no problem. Here's our parameters. We have that n is 10. We're looking at 60% probability of success. We're considering a success to be, we're pulling a receipt that has fries on it somewhere. And then the R value is very specific to the boundary statement. So if you don't want to include that here, that's fine. It's kind of roped up in this. And then for this, I think if you were to think this through, especially relative to some problems that you've done already for binomial distributions, you'd find this one's quite hard. Because this one is dealing with the right tail of a binomial distribution. And if you think about how we use our calculators to find probabilities, we only have two functions. We have binomial PDF and binomial CDF. Typically, if we're dealing with more than one value that x can take, in other words, if x is not equal to something but greater than or less than something, that's going to be CDF. CDF is an accumulation of the bars. C for cumulative in CDF. So we also have to remember that the CDF deals with percentiles more or less, like an accumulation being the left tail, everything up to and including that endpoint. So what about a right tail? Well, it helps to actually have the distribution in front of us. This is that binomial distribution from the problem that I prepared on the side. It's binomial. It's got 10 sample size of 10, and then the probability of success being 0.6. So this tells me that this area under the curve right here is 63%-ish, but this is just by virtue of the app that I have that can do this for me. If I want to get my calculator to produce something like this, because the calculator is all you're going to have on the AP test, knowing that it only gives us the left tail, we can try to do some sneaky complementary event stuff. We should recognize first that the whole x is greater than 5 thing is not inclusive of 5. If we're dealing with a discrete random variable, which we are, our outputs for binomials are only going to be integers, so greater than 5 implies we're dealing with 6 or more. So the complement of this is the thing that's going to include the 5. The complement of 6 or more is 5 or less. We need to be very, very mindful of what the input in our calculator should be. I put this part in dark red here because we don't necessarily need to show this for AP credit. They usually advise you not to write in TI talk and just avoid calculator stuff, but I'm including this in here because this is essentially what you need to be dealing with in order to get the correct probability. And here I have my totally legit TI emulator where I would type 1 minus binomial CDF 10, 0.6, 5. Remember that 5 is included in the complement, not in the area that we're trying to find, so we would be part of what we subtract. Also remember that the input here is n, p, r, NPR like the news station, and watch as it outputs the stuff we want. 0.6331. It's good that the technology is consistent. So in the event that it actually asks for an interpretation as well, oh my gosh, I didn't do it right, no. I refuse to restart the video. You can bust my chops about this later, but there's a 0.6331 chance that more than half of the receipts have fry orders. There we go. So since we looked at a binomial distribution in that app that I just pulled up, it might be worth talking about some forms that the distribution can take. When we describe distributions, usually we talk about center, shape, spread anyway. So we're going to talk about the mean as a measure of center, the standard deviation as a measure of spread, and then we'll talk about the shape. And it's going to really depend on what our two parameters are, n and p. So the x-axis, as you saw, that is our r values. It is the outcomes that our distribution can take. And then the y-axis is the probabilities corresponding to those values. So the formula for this, for the mean of a binomial random variable, is quite easy. It's just NP. And if you think about it, that should make sense too. Like, if I'm talking about a certain population, where like, let's say in a certain town, like 40% of the citizens are female, and I select, let's say like 10 random people, and I want to know about how many females I would expect. Well, I would expect 40% of the 10, which is about 4, plus or minus a little bit, but that's standard deviation stuff. But I'm dealing with 40% of the 10, which is the p times the n. That gives me the expected value, or the average. As far as the standard deviation goes, there's a very interesting proof for this on Khan Academy, but now is not the year for that. I can imagine this video getting really long if I show this. And also, this is not something that you have to remember. Right now I'm going to pull up the stats formula sheet, and then right here under Roman numeral 2, after all this fun probability rules we dealt with. A couple lines down we have, I guess first I should acknowledge this. Since binomial distributions, and then later on geometric ones, since they're discrete random variables, these formulas still apply. But because these are very specific discrete random variables, we get shortcuts. So here we have the binomial distribution with its mean being NP, and the standard deviation being NP times 1 minus P. So I want to note something. Usually when we're dealing with a distribution, or just any kind of formula, the less variables, the better. So I could have written Q as 1 minus P, but I like to use Q as a variable representative of the chance of failure, just because it tends to tidy up things like this a lot. Root NPQ is a lot nicer looking than root NP times the quantity of 1 minus P, especially if you distribute that. Don't do that. But depending on where you go, you might see Q, you might see 1 minus P in place of it. Doesn't matter. It doesn't matter at all. And the more important thing is you don't need to know why this is. You don't even need to remember it. It's on your formula sheet. So if this were a normal year, I'd have you play around with the shape of a distribution and end up calculating these things, which is not too bad. You just take these values and throw them in the formula. And then when I ask you to calculate each of these probabilities, you could use binomial PDF to calculate each of these things. And then if you graphed it, even without graphing it, I'm hoping you can look at these probability of R values and get some idea of what the shape would be. It starts off with a very infrequent probability, and then it ramps up to a climax at 5, and then it goes back down again. We would see that being a cluster around this 5 region, and a very left skew as a result of that. Why is that? Well, it has to do with the fact that the p of 0.8 indicates that we're much more likely to see more successes than failures, because successes are much more likely on an individual basis than failures. Let's pretend that this video edit that I'm doing was a clean cut and a nice transition from one thing to another. Anyway, the next thing to talk about that I wanted to touch upon was acknowledging the shape that that distribution took relative to those particular parameters, and see how it changes if I were to adjust the parameters. Hopefully we could deduce or acknowledge, or now that we're seeing it, recognize that the greater the n, the closer to normal this thing gets, and normality would imply symmetry in a unimodal sort of bell curvy shape. And we see that no matter what p is when we have big values of n. But if we have smaller values of n, like let's say like 15, then we see the odds of, or the probability of success beginning to drastically change the shape of the distribution as it becomes more extreme, as it becomes closer to 1, or as it becomes closer to 0. We start to see a big skew because, let's say the probability of success is 0.92. We would expect to succeed way, way, way more than we would expect to fail, which means we'd have, out of 15, way more successes than failures. So this kind of causes a cluster near 15, and because 15 is where we top out, we can never have more than 15 if n is 15. We start to see it kind of cluster up here, and the opposite of a cluster on the right side would give us a skew on the left side. Vice versa, if the probability of success is very low, we'd expect similar right skew to correspond to that. So to get that down in one place, the shape really depends on the values of p and n, but generally p equals 0.5 gives you exact symmetry, and then depending on how far away you get from that, it gives you a skew left or skew right. The greater the distance from 0.5, the greater the skew, and then the bigger the n, the more normal it gets. So let's suppose now we're looking at a problem that asks us not just about a binomial setting, but also to find and interpret the mean and standard deviation of that binomial random variable. Let's look at this one. 1 year, Murphy's 27 AP Stat students are to be isolated and given 3 unmarked cups. 2 with an off-brand cola, 1 with Coke. The sodas are so similar that students won't be able to tell the difference between the brands, probably because they're all sugary garbage anyway. But let X be the number of students who correctly identify the Coke. So again, according to that practice problem we did a couple pages ago, probably the first thing we should do is identify that this is a binomial setting, aka that X is a binomial distribution, or a binomial random variable. The experiment, or the study, whatever we want to call this, is set up in such a way that we have some markers of a binomial random variable, which is to say that people didn't know which one they were selecting from. They all tasted the same, so the probability that they select the correct one is a solid 1/3. Again, I'm defining Q to be the complement of that, the probability of a single failure per trial. So if success is 1/3 of the time, then failure is 2/3 of the time. And since every student is doing this, we're going to say that the number of trials is going to be equal to the number of students, 27. So the mean value, how many students we would expect to guess correctly, that comes out to NP, which is just 27 times 1/3, or a third of 27, which is 9. And then the standard deviation, there's not too much to this other than throwing stuff in the formula and simplifying. That comes out to 2.45. In terms of interpreting these things, we expect around 9, which is 1/3 of the 27 students, so it's very sensible, to guess correctly. And then this amount would typically vary by about 2.5 students per class of 27. None of this is too shocking if you actually internalize the meaning of things like standard deviation. Pretty standard stuff. A new thing, though, finally, something new. I don't know if anyone's kept up with The Walking Dead. I haven't, but I used to watch it, and back in the day, there was a character named Carl, and he was garbage. He was not a very likable character because he was so clumsy and made such poor decisions in a zombified post-apocalyptic world. So let's talk about that version of Carl. Carl from Walking Dead, at least he was notoriously terrible during the beginning of the show. Suppose he has a 0.2 chance to kill a zombie from point-blank range with any shot. Assume that shot accuracies are independent and have the same rate of success. So let's say he doesn't learn from his mistakes. If he misses, he doesn't kind of calibrate his accuracy. He's just got a 20% chance every time. Come on, Carl. Let's let X equal the number of shots Carl takes to kill some random zombie. So there's one coming at him, and he's just firing shot after shot after shot until he finally lands one that ends up killing the thing. So I'm defining that, the number of shots Carl takes to kill a random zombie, as X. Why isn't this a binomial setting? This is what you should be asking yourself. Well, we don't have a fixed number of trials. We're not going to shoot. Carl doesn't have well, I guess maybe he does have 6 bullets, but he's going to stop shooting once he lands his first success. And that's what defines it as this new thing that we're going to define it as, the fact that there's no fixed trials. The thing that makes it similar to a binomial distribution, though, is that each shot is independent and each probability of success is the same from trial to trial or from shot to shot. So if I want to know the probability that it takes him 4 shots to finally hit and kill the zombie, we should think about what this implies. If his 4th shot is the first one to be successful, that would imply that the first 3 are failures. And we should ask ourselves how often that happens. If P is 0.2, we would expect Q to be 0.8, and the 4th shot being the one to do the job means that the first 3 didn't. So if X is the number of shots it takes to kill a zombie, and the 4th one is the one we're looking for the probability that X, for whatever this new random variable is, equals 4. X equals 4 would imply 3 misses and then a hit, so 0.8 to the 3rd times 0.2, which ends up being like 10%. If I were to ask, find the probability that it takes him at most 2 shots to kill a zombie. At most 2 implies 2 or less. So either he gets him on his first shot, which is going to happen 20% of the time, right? 20% of the time whenever he fires that gun, he's going to kill that zombie. Or it's going to happen on the second shot. And if his success is on the second shot, his first success, that would imply that his first shot missed. So X equals 2 really implies a failure and then a success. So the 0.8 times the 0.2 is 0.16. 0.16 plus 0.2 is 0.36. Since these are mutually exclusive events, we just add them without having to worry about overlap. Told you that chapter 5 stuff would come into play eventually. So again, this isn't a binomial distribution, so we don't have to worry about things like probability of X equals 0. Why didn't I include that in there? Technically 0 is less than or equal to 2, right? Well, we define this differently than we do with binomials. X in this one is representative of the number of trials that occur until the first success. So X equals 0 implies we don't have any trials. So if we don't have any trials, we can't have a success. So unlike binomial distributions, X equals 0 is just not a thing that we have in this new thing that, surprise, surprise, it's called a geometric random variable. So geometric setting arises when we perform independent trials, same as binomial, of the same chance process, same as binomial, and record the number of trials it takes to get one success. This is where it differs. We say R equals 1 always, there's no fixed number of trials. On each trial, the probability, P of success must be the same. So if we try to think about the formula for such a thing, I'll just lay it out because it's on your formula sheet. The probability of failure times n minus 1 times P. Maybe it might help to think of this as P to the first power, which of course we don't need to say. But again, the context that allowed us to derive this on the previous page was recognizing that in order for, let's say, my success to happen on the 10th try, that implies that I would need 10 minus 1 or 9 failures before I get that first success. So 10 minus 1, 9 failures times the 1 success gives me the 10 trials. And this is a geometric setting. It's very easy. You don't even really need to name this thing. It's so intuitive. It's just the number of failures, or the probability of failure time to the power of the number of failures times the probability of success. Speaking of which, in Monopoly, the only, or one of the only successful ways to get out of jail is to roll doubles. I don't know if anyone plays that way or if that's a house rule or whatever. But suppose the player suppose a player has to stay in jail until he or she rolls a double, and we'll let X be the number of times rolled until we get a double on the die. So we should first identify why this is a geometric setting, and then identify the parameter P. Well, this is a geometric setting because we keep rolling our 2 die until we end up with our first success. A success being defined as rolling doubles on the die. The dice, plural. So then the question becomes, for part 2 of this, what is P? What is the probability of success? What's the probability that if I roll 2 die, dice, they're going to have the same face? The answer to that ends up being 1/6. I could lay out the whole sample space of all 36 outcomes here, but really if you think about it, whatever face you get on the first die, the second die has a 1 in 6 chance of being the same as it. So the probability of success, the probability of rolling 2 dice that have the same face, is 1 out of 6. So now to actually use this geometric setting, find the probability that it takes exactly 3 rolls to get out of jail. What about exactly 10? What about exactly n? So if we stick to the formula, this becomes basically just a matter of plug and chug, but also if we think this through logically, taking exactly 3 trials, or 3 rolls to get out of jail would imply the first time we got no dubs, second time we got no dubs, third time we do. So we take the probabilities of these events and multiply them together, and we end up getting like 12%. If I want to know the probability of it taking 10 rolls to get doubles, that would be very unlikely. That would imply 9 failures followed by a success finally. And it ends there because we're done after we get our one success. That's how we define geometric settings. That occurs 3% of the time. So this whole repeated multiplication of failures thing, we could condense that into an exponent, which if we extended this to n rolls, just more or less gives us the formula in the first place. If I have one success, that implies n minus 1 failures, so that would be our exponents, because that's repeated multiplication of q. One more problem here. Or one more page of notes, I should say. If I want to do the same thing with geometric that I did for a binomial setting, which is look at the x and y axis, the shape, the mean, the standard deviation, I'll just tell you right now, the standard deviation is not very intuitive, but it's also on the formula sheet. The x and y axes are going to be the same thing for a geometric distribution that they would be for a binomial one. And the mean is, again, I'll just tell you, 1 over p. This is one of those types of things that the internet has a bunch of proofs for. If anyone's super curious, Khan does a pretty short video on Khan Academy, like 5 minutes, proving this with some pretty fancy algebra, but this is not the time for that. The shape here for a p equals 0.3. So note that for a geometric distribution, there's really only one parameter. It's how likely am I to get a success if I have a single trial. If it's 0.3, we see that this thing is right skewed. And I'll be honest, if p is anything, it's going to be right skewed. Anything other than 0 or 1, I should say. And if we think about why that is, we should think about what each of these bars represents. This is the probability of getting one success, which is 0.3. Here it is. This next one, the probability that my success occurs on the second trial. That's a failure and then a success. So 0.7 times 0.3. So 0.21, we could see it lines up with that. The next one would be 2 failures and then a success. So 0.7 times 0.7 times 0.3. Which what we should begin to notice is that each of these is going to be 0.7 times the previous value. And if I take a value and I multiply it by 0.7 or anything less than 1, that value is going to go down. So what we see is the probability going down and down and down, further and further and further, until we get something that's asymptotic with the x-axis, because if we are infinitely unlucky, we could just not get a success, thus the asymptote, though that probability does approach 0. So what we end up with is a perpetual right skew always, regardless of what our chances of success is, and then also is going to be, like I said, asymptotic with the x-axis. I have some calculator functions here that you would expect to be utilizing in order to solve some problems related to area under a geometric curve. Again, like I said with the binomial one, be very mindful of whether our bar is included in the actual value or its complement. Remember how we handle the whole greater than situations when we take complements. And the whole PDF versus CDF thing, it's the same as with binomial, was the same thing as with normal too. Except we didn't really use normal PDF. But other than that, that's pretty much it. This formula here, as well as the geometric formulas, standard deviation. Wow, sorry. It's getting late. This is not something that I even bother talking about because we're not going to deduce it. You're very rarely even going to use it, but if you do, it's there for you. So just be very aware of this whole Roman numeral 2 thing on your stat sheet. Just be comfortable enough with it where if you need it, you know where to find stuff on the fly. And also be cozy with your calculator. And then if you can do that, you'll be fine. This video happens to be the last one in 2020. I almost said before New Year's, but yeah, that's the last video of 2020. So thanks for bearing with it, guys. I appreciate your viewership, and honestly, with this year being as crap as it is, I appreciate you folks. So thanks for watching.